Welcome back, calculus students. This is part 2 of the video notes on function curve sketching using derivatives. And in this portion, we're going to talk about concavity and introduce some vocabulary words. So we're familiar with critical values that don't represent local minimum or maximum because they don't represent the derivative changing from positive to negative or vice versa. But these points are still considered critical and matter for the shape of the graph. When a graph curves, it can curve upward or downward. This is called the concavity of the function. So over here, where the second derivative is positive, we're going to see functions that are concave up. A function can be decreasing and concave up or increasing and concave up. Similarly, when the second derivative is negative, we have what we call concave down, and a function can be decreasing and concave down or increasing and concave down. And so this table just kind of summarizes that in a neat presentation of information. If f is continuous at a and f changes concavity at a, then the point a f of a is called an inflection point. So here in this graph, we have an inflection point somewhere in between the minimum and maximum where the function changes concavity from being concave up to concave down. And so basically the second derivative is changing from being a positive to being a negative. To test for concavity, you are going to find the second derivative and set it equal to 0. So let's give that a try. We're starting with a cubic function, and if we take the derivative, we're going to get a quadratic 3x squared minus 12x plus 9, and we've seen that we can use this to determine if the function is increasing or decreasing, but we're going to go one step further now, and we're going to take the derivative again. And so we're going to set this second derivative equal to 0. And this is going to help us solve for the point of inflection. Add 12, 12 equals 6x, divide by 6, and 2 equals x. So 2 is when the function changes directions. And we can use a sign chart like we did in the last video, using maybe 1 and 3 or even 0 and 3. So at 1, if we plug in 1 to our second derivative, and I'm going to go ahead and highlight it in this fuchsia color, or mauve, maroon, whatever. If you plug in 1, you're going to get a negative 6, which is a negative value, and that tells you that the function is concave down. If you plug in instead 3, you're going to get a positive 6, and that tells you that the function is concave up. So at 2, we have an inflection point, and the function is changing from being concave down to being concave up. So the intervals where f is concave up are negative infinity to 2, and the intervals where f is concave down are 2, I just wrote that backwards. The intervals where f is concave up are 2 to infinity, and the intervals where f is concave down are negative infinity to 2. Finally, we're going to move on to the second derivative test, and this is the way the test is summarized in our textbook. Suppose that the derivative is equal to 0, that the second derivative is continuous over an interval containing that critical value. Then if the second derivative is positive, you have a local minimum, meaning if it's concave up, you're looking at a min. If the second derivative, that should say negative, then it's a maximum. And if the second derivative is 0, the test is inconclusive, and you're going to find a different way to identify whether it's a maximum or minimum. So let's apply this algebraically to this quintic fifth degree function. Use the second derivative to find the location of all local extrema for f of x equals x to the fifth minus 5x cubed. Step 1, find the first derivative. X to the fourth minus 15x squared. Find a value c such that the derivative is equal to 0. And so if I factor this, I'm getting 0 is equal to 5c squared minus 3. And I've got options at 0 and then at plus or minus the square root of 3. Step 2, find the second derivative. And then we'll take the second derivative and we'll see if it is positive, negative, or 0 at the value of c. So the first thing I'm going to note right away is that if I plug in 0, my second derivative is equal to 0, and I don't know whether it's a local max or min. Then I'm going to plug in my positive square root of 3, and that's going to give me see if I can do this somewhat in my head. 20 times 3 square root of 3, so that's going to give me 60 square root of 3 minus 30 square root of 3, which is a positive value. And so I know that I have a minimum. And finally, when I plug in negative square root of 3, this is now going to be negative. This is going to be positive, but the overall result is still going to be negative. So I've identified that this is a maximum. So let's classify these. We've got a minimum at the square root of 3, a maximum at negative, and we don't know what we have at 0. So for identifying whether 0 is a max or a min, we can always go back to the first derivative test and bust out a little sign chart. Here's 0. A number to the left of 0 is negative 1. A number to the right of 0 is positive 1. And we're going to tell, using our first derivative, whether the function is increasing or decreasing to try to decide. So if I plug in negative 1 into my first derivative, I am going to get 5 minus 15, which is negative. If I plug in positive 1, I'm going to get 5 minus 15, which is negative, and thus this is neither a maximum nor a minimum. That concludes the video notes for our lesson on curve sketching. Thank you for watching.